Okay, fantastic. So welcome back to the course of electrodynamics. Today's will be, honestly speaking, we'll be only discussing about special functions. Okay, we will be going through a couple of special functions that we will be using them in electrodynamics or in general in physics, in the field of physics. And there are tools that you can understand physical properties of different systems, essentially electrodynamics or quantum system or even classical dynamics. So let's start from the place that we stopped, which last time was we discussed about orthonormal functions, so essentially complete set of modes. And I say that it's exactly look like the Hilbert space or vector space of that you define certain, let's say, functions which you know the property of those functions very well, and then you want to expand any functions in terms of them. That's the meaning of completeness. And in the quantum mechanics, this is usually what we go for. I mean, we write it in terms of, let's say, summation of n, and n is equal to identity. That's for discrete version, which shows that really those modes of n, they're orthogonal. And that's exactly the same situation also that happens in electrodynamics or other part of the fields. We just use different notations. We will see that. We will see in a minute. And I say that, look, this is the alphabet that we essentially use it to understand. So let's go with a specific, and we discuss about the completeness and orthogonality. And we say that let's assume a specific case that you have a space which is an algebraic space of X, which is between 0 and 1. And we are looking for orthogonal functions there. Okay. Oh, let's be careful. We are looking for complete set of orthogonal functions. So there are many different ways that you can look at it. And the easy way that we consider, we say that let's consider those modes of un x or function of un of x to be power of x power of n. Okay. Or if I want to be careful, there are cn x power of n, which n is starting from 0, so it will be I. Okay, well, let's go with z plus for those pre-built in. Okay, so that was the definition that we had. And essentially that is look like x power of 0 with c0, and the other one can be completely different one. I don't know, alpha x power of 1 plus beta x power of 0 and etc. And we say that we assume that the linear product which we define between u and v is given by integral of u star v dx, and we assume that the weight that usually we have for special function is 1. This is the one case that we assume here. And we say to ourselves, let's build up some basics of special functions which they are orthogonal to each other, and very likely also they are providing a complete space for us. And we started with the first case. We say that, okay, that is given the first one, which is u0 is equal to u0x is equal to alpha x power of 1, power of 0. And we say that let's first check that u0 is equal to 1. And from here, what we got alpha power of 2 in the domain of 0 to 1. We got alpha power of 2 that should be equal to 1 divided by 2, if I remember well. Right? Was 1 or 1 divided by 2? Let's do the mathematics. Integral of alpha power of 2 dx from 0 to 1 is equal to alpha power of 2 and x from 0 to 1, and then we get alpha power of 2 equal to 1, then alpha is equal to 1, positive 1. Okay. we assume that is plus. So you can go even with negative, or you can go with e power of, I don't know, a constant function. Okay, so we assume that is a real space, essentially, the domain that we consider. What about the second one? The second one, the natural way of thinking, we say that, okay, u1 of x should be equal to beta x power of 1. Okay? What is the property of this function then? u1 and u0 should be equal to 0, and we assume that u1 and u1 should be equal to 1. Those are the two properties that we are looking for. They call, by the way, they call this a Schmidt representation. So we start from the first vector, and then we fix that, we make it normal, and then from this one we build up the second vector, and then the third vector, the fourth vector, and etc. And from the second relation, what we get beta power of 2 integral of x power of 2 dx from 0 to 1 equal to 1, and from here we get beta power of 2 x power of 2 divided by x power of 3 divided by 3 from 0 to 1, and then I think we changed the notation, right? No one said no. We assume that it's from -1 to 1. That was what previously we had. So that was from -1 -1. That is from -1. That will be 1 divided by 2. That will 1 divided by 2 power of 2. So we got alpha equal to 1 divided by square root of 2. And for that one also, that will be changing from -1 to -1. So that it means that beta power of 2, 2 divided by 3 equal to 1. Then from here, what we'll get that beta is equal to square root of 3 divided by 2. Is that right? Okay. So then we got u1, which is square root of 3 divided by 2 of x. And now we have to verify that the u1 and u0, they are orthogonal to each other. And remember that the u0 that we got it from here, it is 1 divided by square root of 2 of, okay, x power of 0, which is 1. And now let's check if whether u1 and u0, they are orthogonal. Let's check this. So then we get integral of square root of 3 divided by 2 times 1 divided by square root of 2 of x dx from -1 to 1, that is equal to square root of 3 divided by 2 integral of x dx -1 to 1, which is square root of 3 divided by 2 x power of 2 divided by 2 from -1 to 1, which is 0. Okay, so clear that the first one, okay, it seems that it's orthogonal. So we don't have any problem with that. Now let's go and build up the other function, the second one, which is u2. And what we are expecting as a u2 of x, it is, let's say, alpha of x power, and say, sorry, gamma of x power of 2. Okay, this is the logical way of thinking. We say that, okay, from the first one, we got that is orthonormal now. The second one is orthogonal to the first one and also is normal. Now let's go with the second, the third function that we want to find, which is u2, and that is should be logical, a cubic, a power of 2 function. Okay, and I don't want to go and calculate what is gamma, but let's do the orthonormality. So I will ask Nazanin to help me. So what it should be the U2 relation with U1 and U0.
So we write the integral from
No, in general, what it should be the relation between these two.
Oh, they have to be 0 because they're orthogonal to.
Exactly, exactly. So let's do the mathematics, and what you will get integral of gamma x power of 2, then 1 divided by square root of 2 of dx should be equal to 0. That is what you have it for u0. Integral of gamma x power of 2 square root of 3 divided by 2 of x dx should be equal to 0. Right? So from the first one, what we will get that it will be gamma x power of, it will be gamma divided by square root of 2 integral of x power of 2 dx. Is that 0? No, this is not equal to 0. So this choice that we do have is not a proper one. While the other one is fine, because the integral of gamma square root of 3 divided by 2 integral of x power of 3 dx, that is 0 from -1 to 1, because the outcome will be x power of 4 divided by 4, and this is an even function, then therefore what you will find out that is definitely 0. So the first problem here is that you cannot fulfill this condition if you only choose the parabolic term, so x power of 2. What you have to do, you have to go with other terms as well, just to satisfy this. So what are the other choices? You go with gamma x power of 2 plus delta x plus, I don't know, alpha, and then you will see if that will be fulfill and sing it. So if you have x term here, then from the relationship that we do have for orthogonality with the second function, it means that you will have an x multiplied by another x that will give you x power of 3 that also will not be satisfied. Okay, it will give you exactly the same the same problem that you had it with the first case. So what does it mean? That definitely as a solution we have to consider only a constant here, or let's say this should be a set of even function. It should be x power of 2n. All right, you cannot get even function and odd function together and then satisfying the orthogonality. Okay, we will see that later on as well. So if you do that, then you will get the conditions that we have. It will be for u2 and u0, that will be integral of gamma x power of 2 plus alpha times the other term, which is 1 divided by square root of 2 of dx equal to, you will get two relations. So you will get gamma divided by square root of 2 x power of 3 divided by 3 plus alpha 1 divided by square root of 2 x from -1 to 1. All right. Then from this relation, what you will get gamma divided by square root of 2 divided by 3 plus alpha 2 divided by square root of 2 should be equal to 0. And 2 divided by square root of 2 goes away, and then you will get gamma plus alpha 3 alpha equal to 0. And from here you will get gamma should be equal to -3 alpha. Okay, what would be the u2 and u1? u2 and u1 will be integral of gamma x power of 2 plus alpha times u1, which is square root of 3 divided by 2 of x dx, and that will be integral of x power of 3 dx plus alpha square root of 3 divided by 2, which is gamma square root of 3 divided by 2 of x dx, from -1 to +1, -1 to +1, which definitely that is equal to 0, because the result will be x power of 4 divided by 4 and x power of 2 divided by 2, which they are even functions, and in a symmetric form that will be always equal to 0. So there is no worry further that we should care. So what is happening, essentially, you are splitting the functions in two forms. One, they are odd functions, the other one, they are even functions, and the odd and even functions, essentially, if you have proper coefficients, they provide you orthogonality among them. So that is what happens. So now we know very well that is the term that you have to choose, and that provides you the orthogonality, which means that gamma should be replaced by -3 alpha. So means that you will get alpha minus 3 x power of 2 plus 1. And now how do you find alpha?
The normalization condition that we have, like the
Exactly.
integral.
So in order to find alpha, you look at the u2 and u2, and that should be equal to 1. What you will get is equal to alpha power of 2 integral of -3 x power of 2 plus 1 power of 2 dx, and that should be equal to 1, from -1 to +1. All right. So that will be 9x power of 4 minus 6x power of 2 plus 1 minus 1 to 1 of these dx equal to 1. So it means that you have alpha power of 2. The first term will be 9. The second x power of 5 divided by 5 minus 6x power of 3 divided by 3 plus x from -1 to 1 equal to 1. And that will be, all of them, they will be 2. There will be a coefficient of 2 at the front of these. So it will be 2 alpha power of 2 of 9 divided by 5 minus 6 divided by 3 plus 1 equal to 1. Have I done any mistakes, guys? Please tell me if. So that will be 15. 14. Okay. Okay. All right. So I will stop here. So definitely the other term that you are looking for, it should have x power of 3 and should have x, right? With the same logic that we discussed. It cannot have x power of 2. It cannot have a constant. So that will be the U3 and etc. So let's review that. U0 was 1 divided by square root of 2. What about U1 of x? That was, I think, we got square root of 3 divided by 2 of x. U2 of x, we got square root of 15 divided by 24 of 3x power of 2 plus 1. And with this fashion, you can build up all of those functions. What are the property of them? They are normal, okay? And furthermore, what is happening? They are orthogonal to each other, okay? So this is what they call it Legendre polynomials. So they are polynomials essentially. They start from 0, x power of 0. You have then the other one, x. The other one is, I think there is a minus sign here. Yes, there is a minus sign here. And the other one is 3x power of 2 minus, with the minus sign plus 1. And the other term will be also x power of 3 and x together, and etc. You have not seen this in this form, right? Have you ever seen this? No. So the point is that this is what mathematicians they are using it, and they are orthonormal functions. What physicists they use, they take U0 of x, then divide it by U0 at 1, and they look at that. What will be the result? And they call this Legendre polynomial, P0 of x. You can do that essentially for any of u. And that is the definition that we do. We just multiply it by a constant. So for example, the P0 will be 1, P1 of x will be x, P2 of x will be equal to, that will be 2. Let me do that one. So it will be minus 3. Multiplied by 1, it will be plus 1. Then the coefficient will be 15 divided by 24. That will be essentially minus 2 square root of 15 divided by 24. So you have to divide this by minus 2. So it will be minus 1 divided by 2 of minus 3x2 plus 1. Which is essentially 3x power of 2 divided by 2 minus 1 divided by 2. Or you have seen this in this form, 1 divided by 2, 3x power of 2 minus 1. Is it familiar now, guys? And etc. You can build up that. So this is the Legendre polynomial that you will get, the set. And essentially, Pn, they are orthogonal to each other, but in this form, they are not normalized. Okay? Be careful of that. Remember, what is the domain of x?
It's minus 1 to 1.
Exactly. Okay. Any functions that is between minus any variable that is between minus 1 and 1, you can have a polynomial which they are orthogonal to each other, and you can expand the function in terms of that. So what is usually happening, and where this shows up, when we deal with cosine of theta. And theta, assuming in spherical coordinates, theta is that angle, and theta is changing from 0 to from the North Pole to the South Pole, which is pi. Okay? So the domain for theta is from 0 to pi. Remember, it's not going from 0 to 2 pi. It's going from 0 to pi. And then what is the range of cosine of theta? Is between +1, which is at the 0, to -1, which is in the South Pole. Okay? So essentially, cosine of theta is look like x for our calculation. Then usually what you will see in physics, you will see usually Pn of cosine of theta, which is the form that usually shows up in spherical coordinate as a sort of orthogonal functions. Okay. Let's have an idea also about the Pn's and what they look like. Legendre polynomials. You have to look at the physics domain, not in maths. Let's go to Wolfram alpha. This is what usually I do. Wolfram. So if you look at the domain that we have, which is essentially from, as I say, it's changing from -1 to +1. And we look at the value of the functions that we do have. So the first one was P0 of x, which was 1. And this function is constant. So I assume that this is the value of 1. So always this function is constant, which gives you a constant value here. What about the second function, which is P1 of x, which based on the discussion that we had in physics is given by x. So this function is changing from negative to positive. It's going to be like this. So it's going, it goes like that. What about the second one, which is P2 of x, which we just found it, which is 1 divided by 2, 3x power of 2 minus 1. That is a parabolic one. And if we look at that at x equal to 0, the value will be -1 divided by 2. So that should be here, -1 divided by 2. And then it will be, the coefficient is positive, is 3 divided by 2. It goes to be like that, a parabolic like this. Okay. At 1 and let me see, at 1 and -1, that value will be 2 divided by 2. That will be +1, and for both cases. That is the form of the function, essentially. And if you look at the other terms, which other terms, I have to look at the relationship for them. In physics, what we have, the other term is 1 divided P3 of x. As I say, that you are expecting x power of 3 and x to appear, and the coefficient that you do have for them is 1 divided by 2 of 5x power of 3 minus 3x. And that function, it's essentially, it is changing from -1 to +1. As we discussed, you expect 0, 2, 4, 6, and etc. to be even function, but on the other side, we expect 1, 3, 5 to be odd function. And you will see that. So, I mean, this is what we have it for P1. And you see that P1 is an odd function. P2 and P0, they are even function. And for P3, we expect to be an odd function. So it starts from -1. I'm looking at the plot just to see what's going on here. It goes here, it passes through 0, because if you put x equal to 0, that will be 0, and then going down and going to 1. So that is the pattern that you do have, the plot that you have it for P3, essentially. And P3x is an even function. So remember that. So when n is equal to n is even number, then this even function. When n is odd number, that will be an odd function. Sometimes it helps you with understanding the symmetry when you do the expansions. Fantastic. So that's the first set. What about the second one? And when, for example, if we have this function, let's say p of n of x, and we know that this p n of x, they are orthogonal to each other, so it means that p n of x, p m of x dx, if you do the integral from -1 to +1, then definitely that is delta of n and m. Okay, that's the orthogonality. However, they are not normal right now. Okay, which means that when m is equal to n, definitely that is not equal to 1, but requires a coefficient that you need to place it here. And we will be discussing about that. This is the way that the normalization that we had, this normalization, destroys the orthonormality. So let me look at the relationship, and we'll tell you what is the orthonormality that you get it for Legendre polynomial. So if you have, remember this, -1 to +1, it's an easy mathematics to do. If you have PL of x and PL prime of x dx, remember that's L prime, that will be delta of L prime. And then as a coefficient, you will have 2 divided by 2L plus 1. Okay? Melika, you have a question? Okay. So essentially, any functions that you do have it in that domain can be expanded in terms of these one. So means that if I have a function of x, and the function of x is domain of in the domain of -1 to 1, then that function can be expanded in terms of p L of x when L is changing from 0 to infinity. Okay. And what is CL? The expansion coefficient. In order to find the CL, you have to multiply both sides. You have to use the above equation, orthogonality relationship. And from this orthogonality relationship, you can find what is going on with the CL. So you have to multiply both sides by PL prime of x dx, and integrating from -1 to +1. And then what you will get a summation from L0 to infinity, CL, PL of x, PL prime of x, dx. And we know that the result of these will be delta of LL prime 2 divided by 2L plus 1. And we get summation from L0 to infinity, CL delta of LL prime 2 divided by 2L plus 1. And that is nothing more than 2 CL prime divided by 2L prime plus 1. It's a delta Dirac, by the way, a delta Kronecker. So then the expansion coefficient, which we just discussed, is given by 2L plus 1 divided by 2 integral of -1 to +1 fx p L prime of x dx. I have not written in terms of L prime because here we ask it for L. Clear? I see that some of you may have questions because you're thinking or moving your hand. Okay, it's clear. It's nothing more than what we do in a vector space. You have either 3 vectors or 4 vectors or 100 vectors, and then you have a function in that space, you expand it in terms of that. That's all. And how do you find the coefficients? You do the projections on those vectors, and you will get that. If PL, they were orthonormal, then there were no coefficients like this. If we were using U, then there were no coefficient like that. This is the way that I say that mathematicians, they look at it. However, remember that appears also in some other contexts when you do the expansions. The PL of X appears as a coefficient of expansions. That's another way that we are looking at the Legendre polynomial, not just building of functions there. So let's do something else. Okay. Can we build up another set of functions? By the way, you can do whatever you wish with using special functions. Those, they have properties, which the property, as I said to you, first of all, they are polynomials. Polynomials is easy to do the integration, so it's fine. There are certain rules for them. When you have, if you look at the property of those functions, they are divided in even function and odd function. That also tells you a little bit more about the physical properties of a system. So those are things that helps us to understand the situation better. Now, let's do something else. So let's consider that we have a range of 0 to A. Okay? That's the range that we have. X is 0 to A. Now I want to define some oscillatory functions in this domain, which they are orthogonal and they are normal to each other and complete. Okay? So when I say oscillatory, the first thing that comes to your mind is
Fourier transform.
is
Fourier transform.
Yeah. What are the Fourier transform bases?
Sine and cosine.
Exactly. Let's go with sine. Is that fine? No, okay, let's go with sine. So I have a sine of something of x, right? N alpha x. And let's see if whether I can, and let's put a coefficient of beta at the front and see if whether this function can be made such a way that they are orthogonal to each other and they are also normalized. Okay, so let's do that. So u of 0, then it should be, I don't know, beta 0 sine of, oh, we can go with general. Let's go with general situation and see whether we can find that un of x is beta of n of sine of alpha n x. And what are the property that un of x and un of x should be equal to 1, and un of x and um of x, that should be equal to 0. If we can build up that. Let's see if we can do that. Okay, so what is happening, that the first one, it will be integral of dx from 0 to a, and then we do have sine of alpha n x, sine of alpha n of x, that should be equal to 1. And from this relation, what we will get is integral of 0 to a of, we have sine. I have never memorized this. I have to try from the beginning. So cosine of, guys, I'm sorry, I'm looking for the mathematical relation between the, oh, that is sine power of 2. So it's sine 2 of alpha n x dx is equal to 1. There is a beta power of 2 as well. Beta power of 2. So what is this integral? You don't like me, so let me do the mathematics as well.
I guess sine to the power of 2 was 1 minus cosine of 2 alpha divided by 2, but I'm not sure. But I can check it.
That is true. That should be like this. Okay. So what I will do this cosine of let's say gamma plus gamma. That will be cosine of gamma power of 2 minus sine of gamma power of 2. All right. And that will be 1 minus sine of gamma minus sine square of gamma. That will be 1 minus 2 sine of gamma. Then means that sine gamma square is equal to 1 minus cosine of 2 gamma divided by 2. That's correct, yes. What we have written here is totally correct. Okay. So good. Now we do have beta power of 2. The domain is 1 divided by 2 of x. All right. That's the first term that we do have. The second term, what is the integral of cosine, essentially? Is 1 divided by 2 alpha n. All right. Sine of 2 alpha n of x from from 0 to a equal to 1. Let's do the mathematics. B power of 2, that will be the first term, will be a divided by 2. The second term will be second term will be sine of 0 is 0, definitely. That will be minus sine of 2 alpha n of x divided by 2 alpha n of a, okay, equal to 1. Therefore, beta power of 2, or beta is equal to square root of 2 divided by a 1 divided by a minus 2 sine of 2 alpha n a divided by 2 alpha n. Okay. All right. Since I'm a physicist, I can skip the mathematics and I can assume something. Let's say that alpha n for me is equal to n pi. Okay. If it doesn't work, then we will solve it in a different way. But let's assume that is equal to that one, or we can just keep it like this formalism because beta is a constant. We know that it's only function of alpha. And later on, we can use the orthogonality just to find out what is the relation. But anyway, let's go and look at the other step. So let's look at the other step as well. But definitely that is a possible assumption or ansatz that we can consider. So look at the other one. The other one tells us that um should be equal to 0, the integral of them. Remember that the coefficient of beta is a function of n. So properly, you have to label it with an n. Okay, it's not a constant in this category, in this scenario. So let's do the mathematics. That will be beta of n, beta of m, integral of the relationship will be sine of alpha n x, sine of alpha n m of x dx from 0 to a. That should be equal to 0. Okay, that is what I got from um and un. Good, fantastic. Let's look at the relationship and see what we can do with this. So again, we have to go to trigonometry. And since I don't memorize things again, I have to do the mathematics. Cosine of alpha plus, not going with alpha beta. Let's go with a and b. A plus b is equal to cosine of a cosine of b minus sine of a sine of b. Cosine of a minus b is equal to cosine of a cosine of b plus sine of a sine of b. I'm looking for sine, then that will be equal to cosine of all a plus b minus cosine of a minus b. That will be equal to minus 2 sine of a sine of b. Therefore, that will be sine of a sine of b equal to 1 divided by 2 of cosine of a minus b minus cosine of a plus b. Is that right, guys? Okay, fantastic. What I'm doing, I'm changing the product of the two because I don't know how to do the integral of the product, but I know what to do with integral of a sine or a cosine. So this is the reason that I'm transferring it to cosine function. So that will be beta of n, beta of m, integral of 0 to a of 1 divided by 2 the first term will be cosine of the difference. So it will be cosine of alpha n minus alpha m, doesn't matter which one, of x, minus cosine of alpha n plus alpha m x. That should be equal to 0. Okay. Can I erase these parts, guys? The part related to trigonometry. I'm erasing these, guys. Okay. Anyway, it will be in the video and you can look at that later on. Okay, fine. Let's go back to the calculation. Then we will get beta, and those are coefficients. The coefficients are constant, so that really doesn't play any role in our calculation. We have to do the integration of cosine and cosine term there. Then that provides 1 divided by alpha n minus alpha m. Okay. Of sine of alpha n minus alpha m of x minus sine of alpha n plus alpha m x alpha n plus alpha m equal to 0. Okay. If you solve this, what you will get from this relationship, you will get the alpha n should be equal to n pi. Because if you just check it out, if you replace it inside, you will get n minus n prime of pi. By the way, that is between 0 and a. I have forgotten that, sorry, my bad. Then that will be sine of alpha n minus alpha m of a divided by alpha n minus alpha m. The other one difference will be 0 minus sine of alpha n plus alpha m of a divided by alpha n plus alpha m. That should be equal to 0. So if you assume that alpha n is equal to n pi, then the first term, I don't care about the denominator. Individual of these two, which will be, let's say you have two angles, right? The angle of A and angle of B, which you end up with the sine of difference and sine of sum. And you assume that for any A, that should be equal to 0. So you say that the first one should be equal to 0 and second one also should be equal to 0. Then what you will get from the relationship here, that alpha n minus alpha m should be an integer times pi. Alpha n plus alpha m also should be integer of pi, because that is for any arbitrary a. Okay? All right. Then that is the relationship that you will get, that alpha n is equal to n pi divided by a. Independent of any a value, the sine of this will end up to be n minus m pi, and that one will be sine of n plus m pi, which for any n and m integer value that will be equal to 0. So the assumption that I had it should be up. Fantastic. If we got alpha n, which is n pi divided by a, then what is happening with beta n will be, that term always will be 0, right? Then you will get 2 divided by a. So the set of orthogonal functions that we do have in the domain of 0 to a is sine, it is, I think we assume is a un of x is equal to square root of 2 divided by a of sine of n pi divided by a. And we know very well that un integral of un of x of x dx from 0 to a is equal to delta of n and m.
Sorry, it's sine of n pi over a times x, right? There is an x there.
There is an x here, yes. Thank you. Thank you very much. Else it will be a constant value. I can give you 100 problems like this just to tell you to build up orthogonal functions in a specific domain. And it's good to learn, because sometimes when you do research activity, you have to be a little bit creative and think about something new. And remember that based on the discussion that we just had, any function in that domain, if x is between 0 and a, any function that you do have it like f of x can be expanded in terms of these new functions that you define, which is Cn of un of x. And how do you define Cn? Will be integral of 0 to a fx un of x dx. The same way, in the same fashion, multiply both sides by of x, integrated from 0 to a, inside of the summation that will give you a delta function. So it means that only one summation will remain, and then the rest can be built up. Okay? You can expand this in even in a two-dimensional way. You can do it in three-dimensional ways, and etc. For example, I can give you a disk, right? Something like this. Well, maybe having that one, like this cup. Okay, has a certain radius, and I'm telling you, define an orthogonal function which is only function of rho in a two-dimensional way. For the phi direction, we know very well that it will be e power of I m phi. Those are the orthogonal sets, which orthonormal sets, which essentially they will be sine of m phi or cosine of m phi, or e power of I m phi. But what about the radial part? Remember that the radial is not going from 0 to infinity, but is going from 0 to a, which is a given parameter. And I'm asking you, can you define some sort of orthonormal functions or complete basis there? And if you do the calculation, you will find out there are so many different functions that you can use them. One of them, for example, is a Walsh function with W. Okay, so these sort of things you can find by yourself, and you can use them clearly in mathematics, and that's something that we use them frequently. Okay. So I'm looking only at the two examples that we just solved, and from these two examples, we want to understand what's going on with completeness basis. Okay. because the completeness has not even been discussed in the calculation. What we realized is that you do the expansion and how to find the coefficients of the expansion. Look at the Legendre polynomial, okay? We say that if x is between -1 and 1, then there are set of p of n of x, which pn of x and pm of x, that will be delta of m and n of, I think that was 2 divided by 2m plus 1. I think it was something like that. And we say that any function of x can be expanded in terms of this, and from 0 to infinity of Cn of Pn of x. And what about Cn? Cn will be given by n plus 1 divided by 2 integral of f of x Pn of x dx. All right. Let's look at the, this was just only the expansions, but there is a condition here where we can cut the series, okay? Or when we are sure that really we get the fx. That is true when you replace it Cn inside of these, then you will get the proper function that you started with. So it means that if I replace Cn here, then I will get n from 0 to infinity of 2n plus 1 divided by 2 integral of f of x Pn of x dx. Remember, what's that? It's just the coefficient multiplied by Pn of x. This is true and only true when this relationship is satisfied. Okay? Let's do something interesting here. So, and remember that the integral is changing, and also the domain of integral is from -1 to 1, -1 to 1, and the summation also is changing from 0 to infinity. Okay. In order to not get confusion, because I'm using x here in the inside of the integral, the summation is over x, so the Cn is independent of x. I'm using another variable for the integral just to make a difference that this x is different from the x of the polynomial. Is that clear, guys? So remember, the Cn here is a constant coefficient, okay? So it means that it's independent of that x. Of course, you are doing the integration. Here, I'm changing the variable from x to y. Let's do that. So that will be, oops. Let's erase it and let me write it in different form just to make it clear. F of y, Pn of y, dy. Okay. Okay, let's do a little bit of changing the orientation, or let's say the setting of this. So what I will do, I will take the integral out. It will be integral of fy, because that's independent of the summation, right? Dy. And inside of that, what I have is all of them, they are depending on n value. So it means that inside of this, what I have summation of n changing from 0 to infinity of 2n plus 1 divided by 2, Pn of y, Pn of x. All right. Again, the interval of y is from -1 to +1. Sorry, to +1. Is that clear? So the left side will tell us that's a function of fx that we started, and the right side, if it should be true and the expansion should be complete and we have no problem, and in order to do that for any arbitrary functions, it should be true and only true when this bracket, this term inside of the bracket, should be delta of x minus y. Or let's say y minus x. Do you agree? Only in this case we can do that. So it means that in order to have such a relationship, and that is what we mean by completeness, that the summation of n from 0 to infinity of 2n plus 1 divided by 2, Pn of y, Pn of x should be equal to, I'm putting a question mark here, delta of y minus x. This is what we call it completeness equation. Okay? Check that for Legendre polynomial. Don't accept anything from me. Okay? Check that for the Legendre polynomial and check it out if whether this is true or not. Let's go back to the other case, which we saw just, which was un of x, and domain was x from 0 to a, and the functions that we derived, they were un equal to, I think was 2 divided by a, sine of n pi x divided by a. And what we found that un of x, of x, the inner product of these two is delta of m and n. All right, that was the relationship that we found previously, which means that any f of x can be expanded in terms of those. So that is Cn of un of x, can exchange it from minus infinity to plus infinity. And how do you find Cn? Cn is given by integral of 0 to a of f of x, un of x dx. Again, if you substitute it inside of that, what you will get summation of n from minus infinity to plus infinity of Cn, which is integral from 0 to a of f of x, then u f of y, u of y of n dx, u of n of x. Then swapping the integral and summation, you will get integral of 0 to a of fy, then summation from n minus infinity to plus infinity of un of y, un of x dy. And that can be true only if this is delta of y minus x, which means that integral of 0 to a of 2 divided by a of sine of n pi x divided by a sine of n pi y divided by A that should be summation n from minus infinity to plus infinity that is equal to delta of y minus x. Okay. I will put a question mark as well here. That is true only when we have this relation, which essentially that leads us to this relationship, which is summation from n minus infinity to plus infinity of sine of n pi x divided by a sine of n pi y divided by a equal to a divided by 2 of delta of y minus x. Okay. For Legendre, I'm repeating myself. Check it out. Okay. So I will stop here because I think you need to have a little bit of rest, maybe 10 minutes, and then we will see each other in 10 minutes. Okay, perfect. So fantastic. So it was, by the way, it was a nice discussion that we had. And now we go back to the following the lecture right now. By the way, for the people that they look at the video, there are a little bit of discussion in the notes about the completeness of the basis. So we had about 20 minutes of discussion related to that. Now we go back to the green function and essentially looking at the term that that plays a role for us. So if you recall, when we had boundary conditions essentially, and we wanted to solve what we call it Poisson equation, which was Laplacian of potential equal to minus rho divided by epsilon naught. And we want to solve essentially that. And that was the entire discussion that we had about the boundary condition. And what we realized, we say that, okay, assuming that there is no charge, but the boundary condition that we do have, which is from S1 to Sn, the surfaces or the boundaries that we do have, then in that region, you do have two functions, essentially. The one of the function was 1 divided by x minus x prime, and the other function was f of x and x prime, and comes from the fact that we say that the green function that we do have, it should satisfy that following two relationship, which was Laplacian of green function should give you a minus 4 pi delta of x minus x prime. And from the other side, g of x and x prime should be equal to g of x prime and x. And we say that, look, if we look at that expression, essentially, we have two terms, which one term essentially is the green function that we know that is associated with the charge distribution. And in order to have the boundary condition to be satisfied, then we do have another term, which with this term, in order to following up the green function, because we know very well that the Laplacian of this term, the first one, always will be minus 4 pi delta of x minus x prime. So what is happening with the second term was Laplacian of f must be equal to 0. And we say that the f function is a function which is just taking care of the boundary or outside charges that we do have. The charges that they are outside, because if you look at the Laplacian of f is always equal to 0, so it means that it deals with no charges in this space. Okay. However, what is the rule of f is taking care of the boundary. So it is important then to solve and learn how to solve Laplacian of f equal to 0. So in terms of Poisson equation, we are solving Laplace equation. By the way, we know the green function. And we already learned how to satisfy few of the boundary conditions. But now we learn how to get the f function inside such a way that you can just replace it for any other scenarios that you may have. For example, I have my room, which is assuming that it looks like a cube, okay? And the surface of these cubes, they are kept at certain potential. We have never discussed that, okay? We kept, I don't know, this one at the potential of 0, that one at the potential of V, that one is a potential of 0, that one is potential of 0, this one is potential of minus, let's say V0 of X, or sorry, maybe X and Y, and the other one, another potential there. So now it's very complicated situation. My room is kept in different potentials. And I know that in order to satisfy this boundary condition, which I'm not talking about any charge distribution that I may have in my room, I have to solve the Laplace equation, okay, which is Laplacian of f equal to 0, which f is the potential that is inside. However, if I take this mag and bring it inside, then I know that inside of this region, then I have Laplacian of phi equal to minus rho divided by epsilon naught. Okay, and in order to solve these, assuming the boundary condition as well, I have to go with the green function. What is the green function for this part? Is 1 divided by x minus x prime, but it does not satisfy the boundary condition. So what I have to do, I have to look for f function that gives the boundary condition, and then summing up with 1 divided by x minus x prime, and then the solution is done. I get the resolution for my problem. So now the goal of this chapter, or this chapter and the next chapter, is how to get the f function in such a way that you will satisfy the boundary condition. By the way, I have not discussed that what is the boundary condition. Is it Dirichlet, or is Neumann, or is a mix which is Cauchy? Okay, that's the goal. Now let's assume simple scenarios. My room is not 3-dimensional. Let's assume that it's 2-dimensional way. Okay, for simplicity, one direction is infinity. Also, assuming that this is what I have. My room doesn't have a roof. It goes to infinity. I like that, by the way, seeing the sky. So that goes to infinity. And I keep in my coordinates, this is x, this is 0. I don't know, that's the length is a. And I keep this one as a potential of V0, that one at the potential of 0, that is a potential of 0. My notation is a bit strange, guys. That is phi equal to 0, phi equal to 0. And here V is equal, or phi is equal to V0. What about the other side? It goes to infinity, and I have no idea. Okay. And assuming that the wall is going to really until infinity, so it's look like two plates that is really long, okay, wide. So, and there is no charge. What is the Laplacian of phi here?
0.
0. Fantastic. And the coordinate that I have chosen is that is z, xz. Okay. I don't talk about y because I know that long y is constant, so it's independent of y. So I have to solve Laplacian of phi equal to 0 for this specific geometry. Okay. And later on, if I take a circle here, for example, which this circle has a certain charge distribution, the only things that I need is looking for the green function of that. As soon as you know the boundary condition, then everything is easy to solve. Okay. Now, I don't consider at this stage, I don't consider the charge density. I will just consider a simple scenario which I have specific potential at the boundaries, which the potential is defined, not even the normal of the potential. Okay, so it's a Dirichlet situation that we do have. So Laplacian of phi is equal to 0, and we have to write the Laplacian in this coordinate, and upon the discussion, the Laplacian should be written in two-dimensional way. So it means that the derivative of phi with respect to x, derivative of phi with respect to z must be equal to 0. All right. So we are dealing with second order partial differential equation. And what is the functionality of phi? Is function of x and z. That is very clear that we know from the physics that we do have here. How do we solve these kind of problems, guys?
Separation of variables.
Okay, let's do the separation of variables. How many people they know separation of variables? I think all, right? Now I have challenging questions for you guys. You will see that. So, okay, in the separation of variables, we assume that phi of x and z can be expressed in terms of, I'm doing this, guys, be careful, as x of x and z of z. And later on, I will ask you a serious question about this. Okay, this is the assumption that I do, that this function, whatever is this, can be expanded in terms of two different functions of x and z. Okay, let's do that. So if you do the mathematics, then you will get the partial differential becomes a direct differential. So it will be 2dx squared. Of x plus x d2 dz squared of z equal to 0. Then you divide both sides by x and z, and what you will get 1 divided by x d2 of x dx squared plus 1 divided by z d2 z dz equal to 0. So this is a function of x. This is a function of z. The sum is equal to 0. So definitely it means that they are constant. Whatever is the one of the constant, the other one should be definitely a negative of sign. All right, it's clear? So because they are independent functions, they are a function of independent variables, variable x, variable z. So since the two variables, they are completely independent, and then the sum of the two always for any z value, any x value should be equal to 0, then this is a constant of this, and that one definitely should be minus that constant. Good? Mahtab? Perfect. Fantastic. And let's solve this. So I assume that mathematically we are not implement. Yes, go ahead.
Sorry, my laptop is going to be turned off. Can you let me in? I'm going to come with my computer.
Absolutely, no worries.
Thank you.
I will pay attention to the screen.
Okay.
Okay, I do see you. Welcome back.
Okay, thank you.
Sure. So then it means that 1 divided by x d2 of x dx squared, that is a constant, which I call it, I don't know, kappa. Okay. And we will discuss about that, what should be the kappa. It should be positive or negative. That is depending on the physics that you are expecting. And the other one is 1 divided by z d2 of z divided by dz squared equal to minus kappa. Okay, so from the physics point of view, what are you expecting for the function to be along x direction? What are you expecting along z direction? Gavin?
I don't know.
So along x, the potential is 0 at x equal to 0. Look at x equal to 0, potential is 0. At x equal to a, potential still is 0. All right. What about z direction? Z equal to 0, potential is, let's say, is equal to V0. Right? But we don't know at z, let's say infinity, tending to infinity, what is happening. Are you expecting the potential to be increasing or decreasing? Definitely decreasing. You are not expecting the potential to be increased, so it should be decreasing. So then I'm expecting from this differential equation, because if I solve this, I mean, immediately you know the solution, right, guys? You can solve that for any values that you are expecting. And I have not put any constraint on kappa. I have no idea what is the kappa. It can be real, it can be imaginary, it can be positive, it can be negative. I have not discussed anything of that. But let's say that for one of those cases, we are solving the problem. And by the way, this is the second order differential equation with a constant coefficient. It's so simple to be solved. And the solution that usually you are looking for is e power of gamma x or e power of gamma, let's say z. Let's go with one of those. So if you go with that, it's a e power of gamma x. Then from the first equation, I will get gamma squared is equal to kappa. So it means that the gamma is equal to plus minus kappa. Okay? And from the, so it means that that will be e power of plus square root of kappa or e power of minus square root of kappa. X. Or some of these two. So if kappa is positive, what do you get? That will be positive, then it means that either along x direction, the potential will be increasing or decreasing. Are you with me, guys? If kappa is positive, then this one, the first one, will be increasing upon changing of x, and the second one will be decreasing function exponentially. But we know that along x direction here, along x direction potential is not changing. Okay? Then kappa cannot be positive. Mathematically, it's true. Mathematically, you can do whatever you want. It's completely right. Kappa can be an imaginary even number. So, or a complex number. It's not a problem. We look for the kappa that is providing the solution to our problem. Okay? What it should be the value of kappa? Negative. So, assuming that kappa, for our case, is negative, I don't know, parameter, tell me a parameter. I'm done with so many parameters that we are using.
Kappa 0. Like,
oh no, God, no, that's terrible. Sorry. Gosh. Alpha power of 2. Is that fine? So alpha power of 2 is positive now, and now with the negative sign, we are sure that this is negative. Okay, so the solution now will be turning e to power of plus I alpha x, e power of minus I alpha x. Remember, alpha is a real function, or real parameter. So essentially, along x is sinusoidal or cosine, okay? Is a harmonic one. We have not placed any value for alpha because we have to look for that. And we have to find that value. So as soon as we know that the kappa is equal to minus alpha squared, then what is happening with the second differential equation, which is 1 divided by z, d2 of z divided by dz squared, equal to minus alpha power of 2 with the negative. So that will be alpha power of 2. Then here, along z direction, I'm expecting e power of alpha z or e power of minus alpha z. Right? Which one do you expect to be a solution? As soon as we increase z here, we expect the potential to be decreased, right? So we are expecting the second one to be the solution for our problem. All right, where did I get this? I get it complete from the boundary conditions that I'm having. Without, I mean, else I have to go with really a e power of alpha z plus b e power of minus alpha z times what I have there, which is e power of I alpha x plus d e power of minus I alpha x, and then summation or any alpha values. Okay, that is really the scenario. But I'm not going through this, although we will be discussing that later on. So that will be the situation that you have to deal with. Okay, from the physical, let's say from the boundary condition, from boundary conditions, we know that e power of minus alpha z will remain. So the other term will be gone because the potential is not increasing. So phi of x and z now is given by for the x direction e power of I alpha x, e power of minus I alpha x, and for the z direction e power of minus alpha z is a product of these, all of those possible cases. Now I have to implement also the boundary condition along x direction. Essentially, along x direction, any of these two will be a solution. E power of I alpha x plus b e power of minus I alpha x. True? That's the functionality along x direction. What is the potential at x equal to 0? Potential at x equal to 0. For any z value, that should be equal to 0. What about x at a? That should be also equal to 0. So then from these two relations, what I will find that a plus b should be equal to 0 because I set x to be 0. And from the second relation, I will get a e power of I alpha a plus b e power of minus I alpha a equal to 0. So first relation will tell me that a is equal to minus b. Then I will factor out the b from the second one. Then I will get minus e power of I alpha a plus e power of minus I alpha a equal to 0. Then this is minus 2i sine of alpha a. So that means that it will be b times minus 2i sine of alpha a should be equal to 0. B cannot be 0 because if you set b equal to 0, it means that also a is equal to 0. It means that there is no solution. That's a trivial answer. And then the only solution that we will get is sine of alpha a should be equal to 0 for any a value that we do have. So it means that alpha a should be equal to n pi. And from here, I will get alpha n pi divided by a. By the way, we knew that, right? We knew that because we already find the orthogonal basis between the set of 0 to a. We already defined that previously. So we could also stop there. Anyway, so then the solution that I'm expecting, it's for x direction, which is a e power of I alpha x plus b e power of minus I alpha x. Then due to the boundary condition or applying the boundary condition, a will be gone, it will be replaced with minus b. I don't care about the constant coefficient at this stage. Then the only things that I know that is given by sine of n pi divided by a times x. So that is the function, or that we will get it function for x, and function that we got for z direction, applying the boundary condition, was e power of minus alpha z. What was alpha? Minus n pi divided by a times z. All right. Good. Then I know that the potential that I do have, what time is it? Okay. Potential that I have, x and z, is given in terms of sine of n pi a x e power of minus n pi a z. What is your freedom here in this expression? What can be changed? Pi is fixed, a is fixed, z and x also, they are variable, is n, which is, remember, n is negative or positive? N cannot be negative, because if n is negative, this term will be exponentially increasing. Okay, so n is element of z plus. Okay, so it means that the solution that you are expecting to get is a summation of n from 0 to infinity, and that is the result that you will get for this specific boundary condition. That's the potential that you have. However, still we have one unknown parameter. What is this unknown parameter? Is an. We still don't know what is an. How do you find an?
Normalization?
Are you kidding me?
No, I'm sorry. Oh,
No,
it's
no
fine.
worries.
That's
Yes, it's
not-
fine. Yeah, it's fine.
That doesn't have any. Sorry.
No, it's almost 5:30 on Friday evening, so definitely we are tired. Okay.
Sorry. It's like so we expand, we have, can we like we have the vectors like by sort of using those orthonormality equations?
Let me help you, okay? That was the potential that we had. How many of boundary conditions did we use? X equal to 0, x equal to a, z equal to infinity, but we have never talked about z equal to 0. So then how do you find an? We say that phi for any x value and z equal to 0 should be equal to v0. And from here, you will get an. So the relationship will be summation of n equal to 0 to infinity of an sine of n pi a x. That will be equal to 1 because z is equal to 0, should be equal to v0. Now I have already given you the hint, right? We previously we define a set of orthonormal functions, and this is exactly that orthonormal function, right? So multiply both sides by sine of m pi a x with 2 divided by a, I think, integrating it. Then from this, definitely that will be delta of m and n. Then you will get an is equal to v0, sorry, integral of v0 2 divided by a sine of n pi divided by a x dx. And from 0 to a, don't forget that. So then you will get 2 divided by a of v0, and then integral of 0 to a of sine of n pi a of x dx. Then you will get 2 divided by a v0. What is the integral of sine is cosine, right? With the negative sign, so you will get minus cosine of n pi a x divided by n pi a from 0 to a. Do a little bit of mathematics and you will get the relationship that we were looking for, which is, I think it should be, let me see. Oh, I can do that. Let's do that. An is not difficult. 2 divided by a v0. That will be minus sine. So cosine at 0 is equal to, let's write it down. So it will be cosine of 0, which is 1. Divided by n pi a. And the second one will be equal to cosine of a. That will be cosine of n pi divided by n pi a. So that will be 2v0 divided by a times a divided by n pi. Then we do have 1 minus, when n is equal to 0, that will be 1. N equal to 1, that will be negative. So it will be minus 1 power of n. Okay. Then we got the relationship. You place it inside and you will get the exponential one. Of course, there are different techniques to simplify this. Usually I do this sort of calculation, but I don't want to hold you for a long time. Maybe I will write the mathematics and I will pass it to you just to follow the integral. I know that you are a bit tired now. It's almost 5:35. So thank you very much, guys. Is there any question? I'm stopping the video. Is that fine? I will see you on Wednesday, and I will be having an office hour on Thursday afternoon. Send me an email. We can have a follow-up discussion about any part that is it might be difficult to you. Okay.